I'm going to be going over the Quick Hull algorithm. So first, a little bit of background. It was initially published by Eddy in 1976, and then Piat published an identical algorithm in 1978. And then as an extension, Barber introduced n-dimensionality, which improved a lot of new applications and became a lot more unique compared to other algorithms. So the main principles of algorithms is essentially just to find a convex hull of a set of points. This would be essentially like wrapping an elastic band around a set of points, and that would be the area. It uses the divide and conquer paradigm, so it reduces the search space each time. And it was by recursively cooling it, and it was inspired by the quicksort algorithm, which shares a lot of similarities, for example, pivot points and the similar time complexity. So the importance of this, convection hulls are especially important in computational geometry, and it has been used to construct Voronoi diagrams, which are used to model difficult problems, for example, the post office problem. Collision detection has been made a lot easier with convection hulls. Concave objects with holes make it a lot more difficult. So where collision is necessary. So gaming is definitely and medical applications are definitely very good points where they need fast and interactive convex hulls efficiently, which Quick Hull is a very efficient algorithm with time complexity O(n) log n. And determining it can be also used in scientific research with defining the animal population ranges. So it does have a very strong importance. So let's just go over the code walkthrough now. This is just initiating all the points on the that the Quick Hull will take in. The Quick Hull algorithm in this takes in a set and will get the left and rightmost points, so the minimum x, and then we'll create a line out of it using a basic line equation. So this is it's shown visually, and that was a good point to say that all of the data presented was generated using the code, and I will show that at the end. So as we can see, it's the left and rightmost point. The left and rightmost points will be on the convex hull by definition, as it's the furthest out. And so now it will split up the line into two sections, one which is above the line and one which is below the line. The one thing to know is the left hull here is just there to run it through matplotlib and show properly. So it will have S1 and S2. It will actually, since the recursion starts with S1, and then we'll go to S2, the algorithm will actually show that. So now into the Quick Hull helper, it inputs SI and AB. So AB are just the 2 points, and it will find the point which is furthest from that. And as you can see, it starts with just returning the base case. There's no set search through, then obviously there's not going to be another point on the convex hull. And so a new line is created, but this time in a different format, which is ax plus by plus c equals 0. And then this can be used to calculate the distance to the furthest point. This is a new format just because of the divide by 0 errors. So now this will also be sectioned into two different sections by finding the distance from the farthest distance from the point, just by getting the maximum using the distance from point to line function, which just takes in this formula, which was using the format that we used before. And so since we've got the point from here, we got p equals the point. We can then use that to go from p to b and from a to p, and create some new line equations from that. And so now that we've got the furthest point from the line, we can then section that off into its own separate sections, where we can see what's above one line and below one line, and it depends on which side it is on. So essentially we've got S1 and S2, and we want to see which side it's on. Meanwhile, the middle bits get ignored. And so from this, the algorithm continues, and this is where it stops, and S2 starts running. And so we've got that now, and that is the complete algorithm.